In this video, I am going to explain very important integrated rate law method. So children, as you know, there is graphical method, there is initial rate method, and there is post-word isolation method, and this is the very important method because all the three discussed above or earlier, they have their own limitations. Like graphical, it has accuracy problem and it cannot be used for the determination of order with respect to complex sections. Similarly, initial rate method, it can be also used for two species, and there is no involvement of time factor. Similarly, post-word method, it will combination of all these three. Now, integrated law method, it has very important advantage that this method can be used for n number of rectangles and n number of products. This is the first importance. And second is, it involves time period. It involves time period, and as a result, we can calculate the amount of rectangles or amount of products after any interval of time. So, first we'll see here. So, assume there is a first order reaction. There is first order reaction. Reaction is of first order. Actually, it can be for any first, second, or third, etc. So, there is A. A is the reactant, and A is changing into the products. Reactant is changing into products. We can say anything, and so you have an idea about the rate law expression. So A will be changes into the products, and so we can write down. So rate of reaction. So rate of reaction is equal to what? Rate constant and concentration of the species. And what is rate? Rate is equal to A will decrease, so it will be minus dx. Let the concentration of A is x upon dt is equal to k A. So this is the starting point of this integrated rate law method. So dx change in concentration, decrease in concentration, d means minute or delta. This is here it is for the average rate of reaction. In case of integrated, it will be delta. So this is there. Now we will this in place of x we may write here a. And so, on rearranging the equation, so this will come to this side. So, the arrangement is to make the factors convenient for the calculation purpose. So it can be written, let be 1 or minus dA upon A, it will remain as it is, it is equal to k dt. This will be question number 2. Now on integrating equation 2 we will get. So we will integrate this. On integrating the equation number 2 will get this. See how. On integrating equation 1 will have minus ln A. ln is natural law. It is natural law and it has base E in the exponential form. So it will be there, and so it will be kp I. So B from both it has been removed by the integration. We will see integration. Here I is constant of integration. Constant of integration, it can be C, it can be I, depending on, it can be anything. Just whenever there is integration, there is a constant used. Now children, at the start of experiment, at the start of experiment, concentration of A is equal to 100%. Concentration of A will be equal to 100%. But after time t, this time t, it will be changed. It will be changed. So, or we can say, at t is equal to 0 means start of experiment. You know, A will be equal to A naught, a standard. This indicates the 100% value. There is the 100% value. So this equation, that will be equation number 3. Equation number 3. So we will put on keeping the value of A in equation 3. So we will put here or minus ln A naught is equal to KTI. This is equation number 4. So here, as t is equal to 0, so it can become minus ln A, so it will become 0, so it will become equal to I. So this is equation number 5. So children, there is the progression in the differentiation and integration. So this will be our the 5th equation. So we will compare this 3 and 5th. So on comparing equations 5 and 3, we will have. So on comparing, we'll have the following. So on comparing equation 3 and 5, we'll have this minus ln A. Minus ln A. Minus ln A here, it will be equal to KT. And it was A naught. So it will be equal to KT. This rate constant, this is the time. And so here I, the value of I, and will be what? It will be, minus ln A naught. Now we'll calculate as we have to compute with respect to time. Or here we write or KT. This rate constant time. So KT will find, and so it will be A naught upon A. This is equation number 6. Now with the result, we will have this ln, of course, ln with, so it will be there. Now this is very important equation to understand. This is K is rate constant, T is time, and this A naught, concentration of reactants at the start of experiment, that is when T is 0, means 100%, and then A means concentration after time T. Now this will modified for our convenience. See how. Now this equation is not to be used in a convenient manner, so we will change. So on changing the equation 6 to log means log base 10. So it will be convenient to use, and so this K will be equal to 2.303 upon T. And ln will be converted to log base 10, and then the two terms, and so here we will have the A naught upon A. This is equation number 7. So this is the final equation to use anything. So see, this K is rate constant. You know rate constant, very important factor. T, it is the time. Then A naught, concentration at the start of experiment. Concentration at the start of experiment, and this A means concentration after time T. So this equation is highly beneficial. Rather, it is of utmost important. Highly important because see the variables: 1 variable, 2 variable, 3 variable, and this 4 variables. So 4 variables are there, children. So you can have the complete control to find out anything. You can find out this rate constant, so you can find out the order of reaction, time, after certain time, what will be the amount of product formed or reactant, then concentration. Suppose if any question is given, so after time t, so at the start of experiment. So this is very important to note, and this is all very important used to calculate or find out the order of reaction.